Hello and welcome to this clip having a look at a classic long answer style question, common to OCR chemistry. It's using electron potential values to explain observations. So what I'm going to try to work on is how you can actually condense down what you write, saying more with less words, in other words. Because what often happens is when people see a large amount of space with, let's say, 6 or 7 marks, for example, next to a question, they can fall into the trap of starting to write long-winded sentences and risk contradicting themselves and making mistakes, saying the same thing twice but in different ways, all that kind of thing. So if we have a look at this question, it says when excess zinc metal is added to an acidified solution of K2Cr2O7, the solution changes color from orange to green to blue. After removing the excess zinc, the blue solution turns green on standing in air, and they want you to use the data to explain the observations. So let's have a quick look at the question. They want you to use the data, so what they mean by that is obviously the electric potential data. They want you to explain the observations. So there's quite a lot going on, isn't there? Orange to green to blue, and then blue back to green. And it also says it's standing in air. So what the question wants you to do is start where the question suggests the reaction starts. So you need to identify the two reactants. So you've got zinc metal and you've got K2Cr2O7. So clearly that means that these are your two reactants. Now, whenever you choose a pair of redox systems from a set like this in a question, the key thing is to make sure that in one of them it's on the right. So this zinc here is on the right of the arrow, and the other one, like the dichromate, is on the left of the arrow. What you can't do is choose two on the right, because what you're asking it to do then is have two separate oxidations happening at the same time, which is not possible in a redox reaction. Then you use the electropotential values to predict the reaction's direction, and use the idea of position of equilibrium shift to justify what you say. So using the data, we're going to go for the minus 0.76 because that's next to the zinc, and we're going to use the plus 1.33 because that's next to the dichromate. So the electropotential for the dichromate and chromium 3 plus is more positive. So as always, the more positive electropotential will represent the half equation that shifts to the right. And the opposite is true for the one that's more negative. So you state that the electropotential for Zn2 plus and Zn is more negative, so position of equilibrium shifts to the left. So you relate this to the color changes that are seen. So from your recall, you should hopefully remember that Cr2O72 minus is orange and Cr3 plus is green. So that would justify the orange to green change that's described in the question. Now finally, it's quite important also to state that what's reduced. So orange Cr2O72 minus is reduced by Zn to green Cr3 plus. Now you could also say it the other way around. You could say that Zn is oxidized by Cr2O72 minus to Zn2 plus. It doesn't really matter which way you come at it, but you need to make a redox statement and also bring the color changes that are stated in there. So that's what I've tried to do in this sentence here. So it also mentions including relevant calculations and equations for any reactions occurring. So that means two things. You need to work out the E cell value, the cell potential, by subtracting the more negative electropotential from the more positive one. So let's do that first. And now we need to think about the equation we need to write. So we're going to combine this half equation containing the dichromate and this half equation containing the zinc. So the starting point here is to look at the number of electrons. So you can see there's 2 electrons involved in the zinc half equation, but there's 6 electrons involved in the dichromate half equation. So the zinc half equation needs to be multiplied up 3 times. So what that does is it balances the electrons out. So then you leave the other one the way it is, you combine the two together, taking everything on the left-hand side in both equations and putting them into one equation, everything on the right-hand side in both equations and putting it into one. And then you cancel out things like the electrons and, if necessary, any waters or H pluses, for example. So what I'd like you to do is have a go yourself. So I'm going to ask you to pause the clip and grab a bit of paper or a whiteboard and follow the same sequence below, this time for justifying the change from green to blue. Now, you're not expected to know from memory what the blue substance is, but you should be able to work it through using the same idea. So if you can pause the clip now, and then you can resume when you're ready. Okay then. So I'm assuming you've had a go at that, and you might not have completed it, but I'm assuming you've had a shot at it. So let's have a look. You start off by taking the green, which is obviously your Cr3+, and the Zn. Now, why did I choose this one here? Well, I know that I've still got zinc metal in my mixture. I haven't quite got to the point where it says after removing the excess zinc. So I'm still in the sentence where it says excess zinc metal is added. So I need something that involves zinc and involves Cr3+. So my clue is that I'm going from green to blue. So the substance I'm starting with has to be green, so that must be the chromium 3+ here, as opposed to the chromium 3+ down at the bottom. So again, zinc is on the right, chromium 3+ is on the left. So looking at the electrode potentials, you can see that the zinc one is still more negative than the chromium one. So the position of equilibrium shifts right for the chromium-containing half equation. The zinc one will shift left, and that will obviously make Cr2+, which must be the blue compound, or solution rather. So then you say green Cr3+ aqueous is reduced by zinc to blue Cr2+. Obviously putting the values in, this time it's minus 0.41 and minus 0.76. That gives you plus 0.35 volts. And looking at the electrons, you can see in the chromium half equation, you've got 3 electrons in the zinc half, sorry, 1 electron, I beg your pardon, 1 electron in the chromium half equation, that's here, and then 2 electrons in the zinc half equation, so the chromium half equation has to be multiplied twice in order to combine and cancel. So the final thing to try and justify is this one. So over to you again. Pause it and then try once more. See if you can get a bit further this time perhaps. Okay, welcome back. I'm assuming that you've had a go at that. Let's see how you did. So starting with my Cr2+, which is the blue solution. I want something that is to do with the idea of standing in air. That's obviously going to be on my O2. So I haven't used this one yet, the third one down. So my two reactants are Cr2+ and O2. The chromium half equation this time is more negative in its electrode potential than the one involving oxygen. So therefore this time round, the chromium half equation shifts to the left in the other direction. And the oxygen half equation is more positive in its electrode potential, so it shifts to the right. So this should match what the sentence up here is telling us. It went from green to blue and then back to green again. So green to blue, then blue to green. So this is the blue to green going from right to left. So you say blue Cr2+ is oxidized by oxygen gas to green Cr3+. And then the E cell value is obviously plus 1.64, and that's your equation. So again, bearing in mind that there are 4 electrons involved in the O2 half equation, and there's 1 electron involved in the chromium half equation, you have to multiply all chromium species up by 4 to enable that to happen. So let's check the mark scheme. So I'm going to take the 3 boxes that we constructed during the course of that clip, and color code them so you can see whereabouts in the mark scheme they match. Now you'll notice that it doesn't mention anything in the mark scheme about POE shifting right or POE shifting left. I would encourage you to maybe keep doing that in your equations and your equations and your answers, because quite often they do ask you to use electropotentials and equilibrium shifts. You would not get penalized for mentioning equilibrium shifts in a question that doesn't ask for them. So to be on the safe side, it's good practice to keep including that. Now, you might also see that I've put an arrow pointing from the left to the right in each of my equations, but in the ones in the mark scheme, they have arrows pointing in both directions. So the arrows should be reversible really, because it's still an equilibrium. What I've done though is to try to emphasize the shift of the position of equilibrium. So either would be okay in an exam question of this type. Okay then, thanks for getting this far. As always, thanks for listening as well, and see you soon.